Welcome to Time to Talk Science and Medicine. This podcast is brought to you by the Translational Institute of Medicine at Queen's University, Kingston, Ontario. My name is Dr. Charlie Highmarch, and I'm an assistant professor and researcher at Queen's.
And my name is Stephen Archer. I'm a cardiologist and researcher and the director of the Translational Institute of Medicine here at Queen's, which we call TIME.
In this series, we're fortunate to talk science and medicine with some of the most accomplished translational researchers from Queen's University and beyond. We want to know what their dangerous idea is, which is a concept that they're working on which, if true, would change the direction of research or alter our understanding of medicine. We also want to find out a little bit about the person behind these discoveries. In previous podcasts, we've sat down with clinicians and basic scientists from Queen's and beyond to discuss a diverse range of research topics ranging from cancer research to studies of cardiovascular disease, bleeding disorders, and the impact of animal care on human and animal well-being. We've even discussed particle physics with a Nobel laureate and healthcare reform with a former dean.
So David Maslove completed medical school and residency in internal medicine at the University of Toronto. He then trained in critical care medicine at Stanford University in California, where he also completed graduate studies in biomedical informatics. One of the things that David does now that's very exciting, he's a senior editor at Critical Care Medicine, which is a journal that's highly prestigious in his field. And he's an expert on big data, which will be relevant to our conversation today. And one fun fact about David that I'll already let out is that he's also a band member of our house band in the Department of Medicine called Old Doc's New Tricks, ODNT. So maybe he'll tell us about that too. But David, thank you very much for coming on the podcast today. But before we get too deep into your science of critical care medicine and precision medicine, I'd like to ask you about your origin story. How did you become a doctor interested in research?
Well, thanks so much for having me on the podcast. It's a real honor and pleasure to be here, and for the opportunity to talk about where my research is today. I guess sort of origin story wise, if we go way back, I was born and raised in Ottawa, Ontario, and spent the formative part of my my years there. Reflecting on kind of influences there, my dad is a lifelong academic, and so that's probably has something to do with the reason that I'm not just a physician, but an academic physician, and that being at a university is kind of a core part of my identity. So that's kind of followed me through many years. So I might say that the other influence in my upbringing was my mother, who worked as a medical librarian at the Canadian Dental Association, and maybe that foreshadowed somewhat my entry into medical training and later into work at a medical journal.
It's interesting. You know, when you mentioned Ottawa, I actually refrained from commenting on the Senators and piling any sort of malice on the city of Ottawa, being an Edmonton Oilers fan and Chicago Blackhawks fan. So I'd let you go on that. But so your dad, I believe we talked about this before the podcast. Your dad was an economist. Is that right?
That's right. And we can talk Senators all day if you like, because I think we're on a 6 or 7 game winning streak right now. But sure, we can leave that aside.
Maybe that's another show.
Maybe that's a different show. Yeah, my dad trained as an economist. He was a professor of economics for many years at Carleton and a dean of public affairs and management. And in fact, I'm sort of the black sheep of the family for not having advanced graduate training in economics. My sister's got a graduate degree in economics, and my brother-in-law is an economist. And so the academic piece of that and the sort of investigative scientific piece of that, I think, has followed me. And I branched off to apply those principles to medicine more than economics. But things have come full circle, and I've begun to explore the economics of peer review and other scientific concepts in the last little while.
Sounds very Star Wars, where you become your father kind of thing. So how did you get from that sort of exposure to academia from your parents to wanting to do medicine? What was the inspiration there?
I think probably more content matter and exploring these sorts of things in my undergraduate degree at the University of Guelph. Thinking back on what sort of got me interested in disease was probably getting interested in evolution and biology. And I had some really kind of interesting professors who taught Darwin and taught evolution and taught biology and zoology. And I think I just really liked that as a scientific concept, and almost even more so as a philosophical concept that was a gateway into thinking about why it is that that people get sick, and how we learn about the ways that people get sick, and how we learned over years to take care of those people. And so, in fact, after that coursework at Guelph, I applied to do a PhD in the history and philosophy of science, which I was all set to do at the University of Chicago, actually.
Stomping grounds.
But I applied simultaneously to medical school as well. I guess one of the few people for whom that was the backup plan. I pursued both, I think, in tandem. And I applied to many medical schools and got into just one of them, and reasoned that it would be much more practical to practice medicine. I couldn't practice medicine without a license, but I could practice philosophy without a license, and so I went to medical school to get those.
We're so glad to hear you're licensed.
Yeah. So do you bring your interest of the philosophy of science into your medical career? I mean, you certainly will to your research, but does it shape the person you are professionally?
Interesting question. I'd like to think that it does, and I've never sort of intentionally thought about it that way, but those principles hopefully imbue the way I approach an individual sort of clinical encounter, and thinking beyond the mechanics of the disease process to what's going on at a higher level.
I certainly, my father's a botanist. He raised me on Charles Darwin pretty much almost, that it was a major influence in me. And even before I wanted to be interested in science, I was very comfortable with those ideas. And I certainly bring that to my profession today.
That is both fascinating to hear and not at all surprising to hear, given what
Just
you've
a bit
done.
geeky.
Well, no, I think it all makes sense with the way your career has evolved, and mine as well, that some of these foundational principles really can shape the trajectory for many, many years to come, and steer things even beyond your initial training.
But did you run into anyone that was a doctor and a researcher along the way, or did you not? Because in reality, many doctors don't do any research. A few do, and some do a lot. But did you have a role model that was someone who's a researcher and a physician, or is that something you sort of came to on your own?
I think I probably came to that later. I certainly had role models who were scientists and not clinicians. And I can remember some very formative experiences working at the Ottawa Heart Institute, actually. There was a lab there run by Professor Rosalind Labo, who did research in biomaterials compatibility and that sort of thing. And I worked in her lab for a few years in high school and university. And that was she was a huge influence, and I think probably gave me a sense of what a science career would look like on its own, and maybe it wasn't until later that I found some people who combined that with clinical work.
So that's a perfect segue to kind of our next question, really, which is we like to ask researchers about their dangerous idea, and really this is asking you what your idea is, your biggest idea that, if true, would disrupt the way that currently people think about.
No pressure. It should disrupt everything.
It should disrupt everything.
Gravity is over. Borders are gone.
Sure. Piece of cake. Well, I probably need to back up a little bit to explain what it is I do in the clinical realm as a doctor, which is to work in the ICU, where we look after critically ill patients. So if you walked into my ICU, you would see a number of patients who are being cared for intensively with a huge amount of staff and resources that are dedicated to their care. And that's because they're critically ill. They have life-threatening illnesses, and they often require life support machines, ventilators, and dialysis machines and other things to support their failing organs while the process that's made them so sick gets a chance to heal. And we admit patients to the ICU with sort of these umbrella diagnoses that, they have kidney failure, or they have respiratory failure where their lungs aren't working, or they've had a heart attack, or they've had a stroke. And our conventional wisdom is that with those overarching diagnoses, we have an approach to all of the patients who meet those diagnostic criteria. And I guess if I had to sort of summarize my dangerous idea succinctly, it would be that that's not true, that each case of critical illness is completely unique. And knowing what the overarching diagnosis is informative, but not fully definitive in determining the best way to treat them. So each patient needs an individualized care approach.
So it's interesting in an ICU, I mostly spent my life in cardiac intensive care units, but I know walking around a medical intensive care unit, you'll have a bunch of people with infections called sepsis or adult respiratory distress syndrome. But what you're saying is, that once you see one patient like that, that's one patient, and the next person might look the same on an X-ray, but have different physiology, need different treatment. Is that the idea?
Absolutely. And you mentioned sepsis, which is probably the best example of this and the one that's sort of nearest and dearest to me. So it's an ancient term, but it's used now to describe a life-threatening state of organ dysfunction that arises as a result of an infection. And we have guidelines on how to treat patients with sepsis. There have been randomized control trials about different treatments for patients with sepsis. But on a physiological level and on a molecular level, it's hard to imagine that every patient with an infection and organ dysfunction in the ICU is suffering from the exact same process down to the level of the molecule.
I'm actually reminded of a previous podcast that we gave with Dr. Tony Sanfilippo, who said that the number of symptoms has broadly remained the same over the years, but the number of diseases has increased. And obviously that's kind of what you're describing, that stratification.
Absolutely. And as we get more and more tools to interrogate a patient's physiology and biology, we see these differences emerge, even though the manifestations that we look at the bedside, as Dr. Sanfilippo has wisely pointed out, kind of remain the same.
And actually, we had another Tony on, Tony Bai, who's an infectious disease doctor, and his big thing is about Staph aureus and also the chronic effects of diseases that are apparently acute infections but have long-term sequelae. But so when you talk about sepsis, just thinking for our listeners, so you would get Staph aureus or E. coli or some bacteria, it goes into your blood, and then it causes all your organs to malfunction. Is that the general idea? Yeah,
and I guess the extension of that is that those deleterious effects are different for some people than others. So a elderly patient who's had a lung transplant who gets a Staph aureus infection might respond differently than otherwise healthy young person who gets a staph infection in some other part of their body. So the clinical manifestations in the disease process are to some extent determined by the pathogen, that bug like Staph aureus that's invading the body, but to another extent, and maybe even to a greater extent, are determined by the body's response to that infection. And that really opens up the door to looking at these very individualistic responses to that insult.
And so if you took us on a walk around your ICU, how many beds are there roughly?
34 at the best of times, but sometimes we're surging beyond our walls.
Don't go all Charles Dickens, best of times, worst of times. So at the best of times is 34, and on a typical sort of day, what percentage of those 34 beds would be occupied by someone with sepsis? Is it a common problem or a rare problem?
It's absolutely a common problem, and there's obviously many, many ways to look at it. There was a researcher in Pittsburgh, Professor Rudd, Dr. Rudd, who looked at this on a global scale. This paper's 5 or 6 years old now. That estimated that there are about 50 million cases of sepsis worldwide a year, 11 million of which are fatal cases of sepsis. And it all depends on a little bit how you define the problem. In our ICU and in most sort of modern Western ICUs, one way to look at who has an infection would be to look at who's getting antibiotics. And point prevalence studies have shown that if you just sort of go to most ICUs and look through the chart on any given day, probably 3/4 of the patients are getting antibiotics.
Interesting, yeah. So 1 in 5 of these people with sepsis will die, and your contention is that of the people those 50 million people that get sepsis, are there like 2 flavors of sepsis or 20 flavors, or is every person? I mean, it would be kind of daunting if every person was unique. I mean, it might be true, but what do you think?
That actually sort of nicely encapsulates the state of the field at the moment, is that we've started to look at smaller and smaller slices, I guess. Instead of taking sepsis all comers, is there flavor A versus flavor B? And as you get more and more varieties, it becomes harder and harder to study using the tools that we typically use to study these things, which is clinical trials. As you'll well know, clinical trials, you need sample size. You need dozens, hundreds of thousands of patients in order to really get a good sense of what the effect of a treatment is. And the smaller we carve up this sort of sepsis pie into smaller and smaller pieces, the harder it is to get that sample size to make a definitive decision about any specific treatment.
And just so I understand, would an example of flavor A versus flavor B, not to take away from the seriousness of the illness, but be two people get E. coli, one gets vascular collapse and has no blood pressure, but their lungs are clear. Another person gets E. coli and develops this ARD, the adult respiratory distress syndrome. Is that like
sure?
Or?
Yeah, and maybe even worse in a sense than that. In that you could have two patients who are similar, who have the same pathogen, who respond very differently, or you could have two very different hosts who respond very differently, or you could have two different pathogens and similar clinical manifestations. So the complexity increases very, very quickly. If you think of people who are very sick from a viral illness like COVID, they're going to look very different than if that same person got sick with a bacterial disease like E. coli or like Staph aureus.
Yeah, and it is interesting. There were some, like when we think about COVID, there were some people, whether you called it sepsis or overwhelming viremia, but whatever they had, some people would get the lung injury, others wouldn't. Some people responded quickly to a few days of support, and others wound up on long-term ventilation. And it was never, we attributed some of that to, you have Delta strain versus Omicron strain, but a lot of times it wasn't that simple. It wasn't the virus.
No, and in fact, the pandemic, as awful as it was for us in the ICU, really was an opportunity to advance this exact science quite a bit. And so there is a researcher in the University of Edinburgh named Kenny Bailey who already before the pandemic was very interested in why some people with for example, a viral illness would get really sick, while others with this similar pathogen would not. And so because there are these inter-individual differences, it's sort of a logical conclusion of that is to look at someone's genome and someone's genes and how they influence their response to an infection. So he developed this study called the Genomic Study, and we actually signed on to it as the first non-UK site to recruit patients into that study. It must have been a couple of months before the pandemic, before coronavirus, the novel coronavirus emerged. So we were already well positioned to study that when the pandemic arose, and then because of unfortunately the great number of patients who were available to recruit into that study, some tremendous science was done as a result that really advanced this hypothesis.
And that sounds like that's sort of right before we go on in the genomic study. That sounds like that's sort of right up your alley, Charlie, is both being from the UK and being a genomics expert.
Yeah, absolutely. I mean, using genomics and transcriptomics to stratify patients is kind of a smart shorthand. It's relatively inexpensive relative to the impact of the data that you get back. And so that's part of your big idea, to try and kind of like genomically or proteomically profile patients to be able to better understand what all the different slices of sepsis are.
Certainly, and it's a great opportunity to sort of apply a sort of big data framework to doing this. If you're looking for differences between individuals, having more points of comparison between them is certainly better. So being able to compare thousands of genes and to do that quickly in a computer is one, like you said, sort of shorthand way to get to some differences. But there may not necessarily be anything sort of magical about those particular biological signals, but they're ones that we can easily interrogate.
I think the real power of that kind of data set is not just looking at the gene expression patterns, which are going to be very, very noisy, especially in a human population. But the moment you start to co-register those signatures to clinical data that you're collecting simultaneously, then you can start teasing out more complex signatures, but ones that are actually meaningful for hopefully sepsis.
Yes,
diagnosis.
absolutely, and
quick diagnosis as well, because presumably you haven't got weeks and weeks to play around with this data. You need a real-time method of actually understanding who's got sepsis and what bracket, what tranche they fit into. And I know that you're working with a company right now that has a fast-moving, real-time way of analyzing this.
Yeah, absolutely. And we've borrowed a lot of these concepts from chronic disease research and cancer care in particular. I don't want to necessarily pretend that they've got it easier, but you're right. If you're trying to recruit a patient into a study and quickly get to an answer, you have hours and minutes to get to an answer about what treatment they should get, rather than we can take some blood and sequence your genome and see you back in the clinic in a couple of weeks or a couple of months. That luxury of time is not something that we have in the ICU. And so there needs to be a way to downsize that kind of genomic application to something that can be done on a piece of equipment that sits in the ICU and gives you an answer in minutes.
It was interesting. We did not self-promotion, but just as an example for the listeners, we did a transcriptomic study of SARS-CoV-2 and basically looked at all the genes whose expression was changed within 2 hours of being exposed to that virus. And what jumped out, maybe reflecting my bias, is mitochondria. So the phenotype of these people's cells, not the people, but the cells, was that there were vast changes in mitochondria within 2 hours of exposure to the virus. So I guess you could then imagine a clinical trial in which you said, well, if we had mitochondrial therapeutics, we could say, well, you're a mitochondria phenotype COVID person. Now you're not. You're more of a endothelial cell injury kind of phenotype person, so we're going to treat you with something different, or at least we're going to analyze your data differently in this clinical trial.
Yeah, exactly.
That's sort of the idea.
Absolutely. And it dovetails exactly with what we see in sort of bacterial sepsis as well. There are studies now that are decades old that show if you inject someone with bacterial endotoxin, which is the bits on the bacteria that make you sick right away, the 80% of the genome in the white blood cells is repurposed within a couple hours in a similar sort of way. That challenge is the way in which it dovetails into that question about how many different flavors of sepsis we have, because in order to get a determination about which treatment is going to work, you need a lot of patients. And the thinner you slice that pie, the fewer patients you've got in each group.
And I think one of the importance that maybe our listeners might not be thinking about, they might be thinking about your dangerous idea being when to treat. But of course, within the context of choosing wisely, when not to treat is also critically true, because you don't want to waste time, resources, or treat somebody when they don't require treating. So actually, it's working out when not to treat too, right?
Absolutely. And in fact, that's a huge emerging concept in the ICU as well, not only because certain treatments will be ineffective in critically ill patients, but worse than that, they will be deleterious. So if even treatments that are helpful to patients will have these adverse effects and side effects that can lead to prolonged illness and slow recovery and these sorts of things. So not only do you want to avoid things because they might not work and that would be wasteful, they need to be avoided because they can cause harm.
So have we reached the point in science and medicine in the ICU where you can give me an example where, based on personalized data, we do this, not that, for two diseases that have the same name?
Watch this space, I think I would say, is stand by, and we're starting to do those studies a little more after 10 years or more of thinking about this. So the short answer is probably not yet in a guideline sort of accepted way that would mirror some of the things that we see in cancer. But we now have funding from various international groups and bodies and collaborators worldwide to do this very sort of thing, is try to determine at the point of care what type of organ failure you have, and then take those patients and randomize them into one treatment or the other to try to get a sense of whether they'll be responders, basically.
So the vision is there, and the science is coming to eventually make it so we do every patient in that 34-bed ICU might be getting a customized cocktail that is somehow guided by their omics mixed with their phenotype and their personal data to say, oh, not this drug, this drug. So and the part of the philosophy background reemerges here, because my temptation is always to sort of think of that to its further conclusion, not based on experimental results or anything, but if that works for and we like to call these things treatable traits. So if you have a trait, an illness trait that can be treated with medicine A, you might also have a trait that can be treated with medicine B, and so on and so forth. And then there's acute treatments and treatments while you're recovering. And as that list gets longer and longer, the complexity of delivering that care increases, but maybe even more importantly, the complexity of determining if those treatments are effective is a huge thing to tackle. So we're going to go on to our next question, and that pretends that Charlie and I are high school students and have you explain something about critical care to a high school student, which you may have to make it even more complicated because Charlie and I are probably your lowest common denominator. But one of the things you mentioned when we were chatting before the podcast that I found interesting is the best ICU admission you'll ever have is the one that you avoid. So if you're talking to high school students, because what's the mortality rate in the ICU roughly?
It varies from unit to unit and based on your admitting diagnosis, but anywhere from 10 to 20% probably for all comers in the ICU.
So sort of 1 in 5 people that go into that unit, despite all this work, custom nursing care, custom doctor care, very low patient-doctor ratio, die. And so what would you tell us as high school students? How do you avoid winding up in an intensive care unit? Is there anything you can do to prevent ICU admission?
Well, this is sort of the next natural progression of this thinking about individualization of critical illness is as you can see, sort of going down this rabbit hole of the complexity of it all. There are a lot of challenges to sort of sorting that out, which isn't to say we shouldn't charge on and figure those things out, because I think we can. But it also maybe is an occasion to reflect on the fact that if these are such entrenched problems that are difficult to solve, maybe it's better to avoid people getting into this position in the first place. And that's a much newer area of research for us, at least. I mean, it's a concept of primary prevention is by no means new in medicine, but applying it to the ICU is maybe a bit more novel.
So what's the vaccination for ICU prevention?
Yeah, and vaccination is actually probably the guiding principle here in how to study these things. We as intensivists react to diseases that are already there. We know how to study those scientifically and in clinical trials, but perhaps we need to borrow a bit from the public health experts and the field of epidemiology to look at things in that light. How could you, and then in inverted commas, vaccinate people against certain critical illnesses? And there's probably a whole slew of answers there. Some of them are, we see patients in our ICU who have been involved in motor vehicle collisions. And so efforts to get people to wear seatbelts have been extremely helpful in
Do you hear that, kids? Put on your damn seatbelt.
And that's made a difference, right? We tend not to think of that as a critical care intervention or something that's even the purview of critical care researchers, but perhaps it is.
As a cyclist, I'm going to use the same and just say, kids, wear helmets when you ride a bike. Right? It makes such a difference.
We see closed head injuries, and there's we see spinal injuries from people falling off of ladders and so on and so forth. So there's one piece there that's related to just kind of general safety measures. The ones that get more interesting to think about are how to invent a vaccine against, kidney failure, lung failure, really bad inflammation, these sorts of things, or a vaccine concept.
Yeah, and it's interesting. You'll be happy to know this because as doctors, we all like to believe we're influencing the world for good. So you and I had this conversation earlier before the podcast about prevention, and you were mentioning about ruptured intracranial aneurysms that lead to subarachnoid hemorrhage and often result in very long-term disability. And yet 1 in 10 people, if you have a family member that has a subarachnoid hemorrhage from an aneurysm, you got about a 1 in 10 chance or more that you'll have one too. So you'll be happy to know, David, I actually ordered a screening MRI angiogram on one of my patients based on talking to you because she said, am I at risk of having an aneurysm? My mom died of one. I said, well, yes, you are. So, I mean, that's another way in theory of preventing.
Absolutely, and it's really cool to hear that you did that, right? Because that's not clinical cardiology, and it's not intensive care medicine either. But maybe it should be, and I think we maybe need to reframe our positioning a little bit to look at those sorts of things. We're not used to doing that in the ICU, and maybe most cardiologists, not all, are probably not used to doing that in the cardiology clinic. But identifying an aneurysm that can be treated before it ruptures is obviously better in every possible imaginable dimension than treating it afterwards. Even if it cost $1 million to repair an aneurysm before it ruptured, you're still probably ahead.
Well, for our listeners, if you wanted a kind of a perfect example of integrated healthcare, that was it. So every professional has a bump in the road story when it's not gone to plan. And of course, we're all very good at self-promoting and say when it's done well, but I think it's really useful to get involved into what happens when it all goes a bit wrong. What's your bump in the road story, David?
It's hard to pinpoint just one.
We only have limited time in the studio.
David, are you on a road or is it more of a cart path?
Well, that's what I was going to say. It's maybe more that the road we're all on sometimes feels like it could do with a repaving into that very that smooth blacktop that we like to ride on. And that's just, I think, a function of the way our system of research has evolved over years, probably for good reasons, but that create a bit of a productivity gap in what we do as researchers, which I think would resonate with scientists, whether you're here or at any other institution in the US or in Europe or anywhere. There's a lot of work that a investigator does or the head of a lab does that doesn't necessarily translate directly to scientific output, and that just relates to a lot of the bureaucracy, basically, of research that I think is a huge opportunity for improving productivity in a lot of what we do.
How do you think that can be improved?
Well, I wonder, maybe I'm only saying this because I'm someone who's worked without an administrative assistant for most of my career, and some of that is smoothed over when you have a bigger team that can handle additional sort of non-scientific tasks. But I'm just reminded of the fact that, every year I have to renew certain contracts and I have to redo certain training modules and I have to renew ethics applications. And there's, all kinds of agreements that have to go in place to start a clinical trial. All of these things are necessary in order to ensure that we're doing research in an ethical and reliable way. Whether there is some rebalancing that needs to be done is I think, an important question to ask. And there may be some very low-hanging fruit along the way there. So as we talked about earlier, one of my other hats is as a journal editor. You'll both know that getting papers published in journals is difficult. And for reasons that...
Too soon, David.
Too soon. We're just on the back of one.
But for reasons that extend beyond the scientific, right? So you may apply to a journal and they have very strict formatting requirements that say in your references, we want to see the names of the first 3 authors of the paper and then abbreviate the rest as et al. And if that journal turns you down and you submit to the next one, you might submit the same paper and 3 days later they get back to you and say, you know what, in our journal, we like to see the first 5 authors, and then you have to abbreviate the rest. And so somebody spends time redoing some formatting, or, the margins should be 2 centimeters instead of 2.5 centimeters. And these sorts of things are, I think, areas where there's a productivity gap and where there may be some easy solutions.
Well, I think it's a massive barrier to kind of getting this important work out there, because if you have, each paper is like a small brick in a wall, and unless that brick gets laid, it can't be used by other researchers to progress. So the longer it takes to publish a paper because of that bureaucracy, the worse it is for society generally.
Absolutely.
Yeah, I think what the public doesn't know, probably fortunately, although they will know after this podcast, is you might think the hard part is figuring out how to treat flavor A versus flavor B of sepsis. That should be the hard part. And that is hard. But in addition to that being hard, the bureaucracy of getting that study approved, funded, accumulating the money to hire the talented people that are the admins you need to actually deal with the paperwork, that is equally difficult as solving the problem. And so I don't know what the answer to that is, other than that some bureaucracy simplification would certainly help most university researchers do their job.
Yeah, and a general sort of fresh look at what is helping and what is hurting. So, obviously when we enroll patients into clinical trials in the ICU, often they're on a ventilator, they're sedated, they can't give informed consent themselves. So we approach their family members or their decision makers, their substitutes, in order to get consent. That consent needs to be informed. The substitute decision maker needs to have the study explained to them. They need to have the opportunity to ask questions and get answers. And so we have consent forms that sort of document this process. In the last couple of years, we've seen that the requirements for those consent forms are getting more and more complex. We see consent forms that are 10, 15, 20 pages long. And on the one hand, that is maybe helpful because it's potentially providing some more information, providing better reassurance that this process has happened correctly. But if you put yourself in the position of someone whose loved one is in the ICU and you're being approached with this 17-page consent, are you really, are we doing something that's helpful for the patient and their family member there by documenting all the things that we think we need documented? Or is there a way to streamline this into simpler language that better conveys the purpose of the study to them in plain and simple language that might also result in a shorter consent form?
Yeah, it's a little bit like the Apple sort of, do you agree with this? Because if you don't, you can't use it. It's like once it's 20 pages long, everything is hidden in plain sight.
Yeah, and my worry is always that someone will skip ahead, right? And so they'll say, even at the best of times, I just don't have it in me to read 17 pages, but you've got me at a time of vulnerability right now where my mind is elsewhere, obviously. I'm just going to go to the last page and either sign or not sign. And both of those decisions are not really informed. Whether they agree to, if they agree to participate, that has to be an informed choice. And if they agree not to participate and to forego the opportunity, that also has to be informed.
Okay, so on to our next question here, which is getting near the end of our podcast, which is the crystal ball question. So it's 2025 now, and in 2035, when you walk around your intensive care unit, there'll probably be 35 beds instead of 34. So we'll have made that progress. The border to the United States will be back open again. So there'll be new administration in town. So hopefully that will all be better. But what do you think is going to happen? How far do you think you're going to get with this dream of personalized ICU medicine over the next decade?
I'm hopeful that we'll make progress. I think there are so many signals that we can begin to exploit, and pairing that with these great emerging technologies in data science and artificial intelligence, that combined with the incredible networks that we participate in both nationally and internationally, that we can actually get some great science done and some great work done. And your listeners may not know that Canada has always been sort of a world leader in clinical research in the ICU. We have the Canadian Critical Care Trials Group, which was really established the model for how to do this collaborative investigator-initiated research in the ICU. And other countries have sort of adopted that model, and all of those groups work seamlessly together. So that problem that we alluded to earlier about getting the big sample size, we've done very well at actually doing that, and can now do studies where we recruit 3, 4, 5, 6,000 patients in relatively short order. So I envision a situation where maybe we're able to get studies like that going with a more a distinct patient group, and it may be that there's a device that sits by the bedside, and we take a blood sample and put it into the machine, and it says your patient is more likely to respond to treatment A, and so we randomize them to get treatment A or not. And those signals could be from blood tests, they could be from the bedside monitor and looking at very millisecond variations in heart rate and blood pressure. It could be all sorts of things. It's a very data-dense environment, and with the advances that we see in data science, I think the sky's the limit for us there.
So it'll be Siri saying, David, that's not the right dose of vancomycin. David, we've discussed this before.
Siri is going to be busy reformatting my manuscript into another journal.
Well, as long as she has a job.
Is that happening? Okay, so before we wrap this podcast up, this is the fun bit. We like to, for our audience, to get to know a little bit behind the person. And we've got a few silly questions that really kind of dive deep. And Dr. Archer already mentioned a music question, which I'm going to defer back to him. And I'm going to start with food. What is your favorite meal? But importantly, can you cook it yourself, or do you have to rely on somebody in your life?
Oh, boy. That changes day to day. And hearkening back to just the most recent experiences, I think I'm determined to be able to cook my own really great food, and made a cacio e pepe pasta this past weekend, which was quite good.
Well, yeah. That's pretty cool. Okay, good.
Plus an A+ on pronunciation. That's very, very good. So you play in this band, Old Docs, New Tricks. What instrument do you play, and what's your favorite song?
Well, I'm a guitar player. I was going to say by training, but I guess the last time I had formal training in guitar was as a wee child. I actually found that I got a lot better as a guitar player when I stopped taking lessons and just kind of started learning the stuff that I wanted to play for myself. So came into the band as a guitar player, was kind of arm twisted into becoming a bass player out of necessity, and I've really learned to love that. And it's been a great journey to sort of first translate guitar playing skills to the bass, and then more recently try to think of the bass as a different instrument rather than just a guitar with 4 strings.
That's probably helpful.
Well, I mean, certainly as somebody who's kind of enjoyed the Department of Medicine awards party several years in a row, you're kind of as synonymous with the holidays as Mariah Carey at this stage for me. So what's the strangest job that you've ever done?
Oh, that would probably have to be bingo captain.
Cool.
Probably by a lot.
Do you remember any of the calls?
So whenever I tell people that I worked in bingo, they sort of wonder if I was the person actually calling out the numbers and the letters. I was the behind the counter guy who was selling bingo cards and kind of running the business side of the operation a little bit. That was again long ago in the days when bingo parlors were very smoke-filled rooms, and I probably
they were a risk factor all in their own right.
So that's like a callback to the prevention right there.
Kids don't go to bingo.
Don't go to bingo parlor.
Mission accomplished.
I'm sure they're all cleaned up by now.
So here's our next question: if you could travel in time, would you travel forward or backwards? And if so, to where? In the future or the past?
Oh boy, I feel like this question's a bit of a Rorschach test for are you a glass half empty, half full kind of person? I'd be tempted to travel back to a whole bunch of different times and places, but would be remiss to pass on the opportunity to travel into the future and see where all of this stuff leads, all of the work that my colleagues do, and the great science that we all contribute to. And wonder a little bit what it would feel like if a scientist from 100 years ago could travel to the present day. They probably would be astonished, basically, at what they see. So
I'm with you. We get a lot of people on the podcast to answer that question along the lines of, they're all historians. They want to go and see that. I'm totally with you. I would love, and in line with that, I'd love to see what Darwin made of our science today, because he made predictions that hadn't come to pass at that point, which are spot on. It would be, for us to see 100 years in the future would be so cool.
But David, if you go 100 years forward, there's just going to be a box. There is not going to be a doctor at the bedside. It'll just be Siri.
Well,
it's like, unlike Dr. Maslove, I'm going to give you the right dose of
absolutely, and I almost hope that that's the case for a slightly different reason. I've sort of always been of the impression that a doctor's main research goal should be to put themselves out of business, and so that again is a callback to that prevention thing. So it's less that I would want to be replaced by a box, although that's fine. I could spend the time cooking cacio e pepe and playing guitar. But I more want the doctor to be obsolete because they're not needed, that we've figured out how to prevent.
So I'll ask a most important question. If you were a cartoon character, which one would you be and why?
Oh, geez.
It gets harder hitting as the podcast goes along.
Oh, boy. It's I need to think about that one first. The first thing that comes to mind, which is probably not the best thing to convey, is that Far Side cartoon from many years ago of the kid who's trying to get into the school for the gifted by pushing on a door.
I'll take it.
Gary Larson would be happy.
Yep.
Dr. Maslove, on behalf of Dr. Archer and myself, I'd like to thank you for taking time to talk to our audience today about your research, your discoveries, and your thoughts about Canadian science in the future. Also, to our listeners, I'd like to thank you for taking the time to get to know Dr. Maslove with us. We hope you enjoyed the show. If you enjoyed this episode and would like to know more about research at Queen's University, or indeed to share this podcast, you can search for Time to Talk Science and Medicine wherever you normally look for podcasts. Thank you very much.
Thank you.